this is slightly so we were listening to talks on solidification and the liquid to means liquid to solid transformations. So here we will talk more on precipitation, particularly precipitate growth and coarsening, and we'll also introduce the means how to couple elastic stress effects. Before we have seen how temperature field was coupled. Now here we will couple the elastic stress effects, and most of the examples that I'll means all the examples that I'll show are for isothermal in isothermal conditions, precipitate growth and coarsening. Okay, so this is the idea. So first of all, so one of the things Shodav is also online. One important thing that I want to tell is that Shodav has done a lot of development, and one problem that I have in my computer is that I can't directly open ParaView. So I will run the simulations, but I may require some help from Shodav Shina for seeing the simulation. So here the talk is restricted. So currently the model that you have, that it is developed on, by the way, this is developed on CUDA using CuFFT library. So CuFFT is a CUDA library. I'll tell you more about the CUDA and how to basically install CUDA. So we will tell you all those stuff. So currently the library has elastic stress effects. It has precipitate growth and coarsening. It also but it is currently we are looking at binary alloys and two-phase system. So this is a typical microstructure. So you have this alpha phase, and you are at say temperature T1, and then you quenched it at temperature T2 and held it there. So let me just open a pen here. So you were here, now you quenched it here, and you are holding it here, and you are seeing this beta phase that is coming out as precipitates, and these precipitates are growing and coarsening. So this is an experiment that is a very classical experiment in nickel aluminum system from Ardell Nicholson Eshelby's paper in 1966. I think many of us have seen this paper, and you could see this very nice nearly spherical precipitates. They become cuboidal after long-term aging, and after further aging, these cubes grow, and then the cubes also become more like rectangles. As you can see, they become like very thin plates as you continue to age. So this is the idea. This is something that is there in superalloys, and superalloys are in general very important class of alloys, and not only for superalloys. If you look at aluminum alloys, titanium alloys, precipitation is one important process, and this is, and also we are looking at diffusion controlled precipitate growth and coarsening in this part. So here, although we can in principle couple it with CalFAD, and we are also doing that using thermowriter. So we are talking to Abhik about that, and we have already developed the Newton-Raphson code also on CUDA. However, we haven't yet put in the final form. So we need to do some more checks, and we'll put it soon. And so you can directly use the TDB files as Mohan was showing previously. However, Abhik and Kellner and Nissler, this paper shows that even if you for example, when this PyCalFAT was, PyCalFAT is also a recent development, and TDBDB, we found that there are several open source databases. However, several databases are not open source, and you have to rely on Thermocalc or Pandat to look at the values of the free energy, and values are listed in a very scattered way, and you don't really get exactly, you cannot fit a line, very smooth line through those points and stuff. However, there is one very important thing that you can do, since you know the equilibrium you most in all systems, you know equilibrium, and you know the equilibrium compositions. If you can basically use, as they suggested, you can use a very simple Taylor expansion where you have this is the free energy per mole, and this is the derivative, right? This is the slope of that free energy, and this is the curvature. So you can basically use these values. You can use these values, and basically, and you can have this molar volume, and you can fit and you can get this free energy curve for alpha phase, beta phase, means all the participating phases. You can get a nice parabolic approximation of this curve. So you can see this is a parabolic approximation. In fact, Abhik has let us shown that at an isothermal temperature, if you can basically adjust some of the coefficients in the parent the alpha phase, then basically you only require this this curvature term and the equilibrium compositions. So once you do that, then basically you can use that these parabolic free energies, which are much more simple to implement. And as you see that since these are parabolic, the equations become linear, and you don't have to use Newton-Raphson method for calculating the equilibrium at interfacial equilibrium. So here we are using a more idealized version, but you can use any equilibrium value. We are using a scaled equilibrium value, and the scaled composition is such that whatever be your equilibrium, whatever is your equilibrium value, you are basically telling when C prime equals to C alpha equilibrium, then this C becomes 0, and C prime equals to C beta equilibrium, this becomes 1. So we are taking 0 and 1, but in our code we have seen that we can use any values. We can use 0.4, 0.5, whatever. So but in these examples we have used I think 1 or 2 examples I have used also different other values and other curvatures. So all are possible. So you can do that, but these are mostly parabolic approximations that we have used. Obviously, there is a lot of deviation from this parabolic approximation. Then you require to go to the real free energies, which is definitely one of the features that will be included in our next release. So in precipitate growth and coarsening, particularly, what are the factors that influence microstructure evolution? One is supersaturation that we know. Another is interfacial energy. Interfacial energy in our model, currently interfacial energy is isotropic. However, using the same definition as Abhik, or using because we have already developed, Tushar has already developed this extended using Abhi and Hyder's model. He has already developed this fourth order terms, the higher order terms in the Cahn-Hilliard equation. Not in the Cahn-Hilliard equation, in this case in the phase field equation, to introduce anisotropic, cubic anisotropy in interfacial energy. However, the current code that we have released has isotropic interfacial energy. But we also have elastic energy, and in elastic energy there are two features that are added. In elastic energy, we have when we describe elastic energy for this precipitate growth and coarsening, when we have two phases alpha and beta, the major parameter that comes in the first means which gives all the first order effects. That is one of the major first order effects is change in shape with increasing size, right? Change in shape of the precipitate with size. So one of the, and that is mostly controlled by misfit strain. Okay, and misfit strain is nothing but the difference in lattice parameters between phases, assuming the phases to have coherent interfaces. Even if they are incoherent inclusions, then also there can be a volume, because of volume mismatch, you can basically include an eigenstrain, although coherency strain is 0 in that case. So, and you have also elastic moduli. So here we are using cubic systems, but if, as you can see in the code, we can use cubic, isotropic, and tetragonal systems. So we can use, if we use isotropic, then I have to basically specify C11 and C12, because C44 is equal to 2C11 minus C12. And such, and in isotropic systems, as you can see, this is a Zinner anisotropy parameter, and this becomes 1, right? Because 2C44 equals to C11 minus C12. So and another thing is and for tetragonal systems, you will have another additional parameter, right? An additional independent elastic modulus. So you can go up to tetragonal. So both all. On the other hand, another very important thing that is there in our model is that we have used homogeneous modulus approximation. I'll tell you what is that. However, we also have a code that is means we have developed the code for inhomogeneous elasticity when the phases have different elastic moduli. Okay, they can have different elastic moduli such that they have different anisotropies, or they have different shear moduli. So all these things are possible. So you can include that. However, that is coming in the next release. In this release, we have used homogeneous modulus approximation. That is, there is misfit strain, there is anisotropy in elastic moduli. However, elastic moduli for both phases are equal. Okay, so yeah. So already it has been discussed from morning, so I don't want to bore you too much. So as you can see in these precipitation models, you require a non-conserved order parameter field or the phase field, where phi r is equal to 1 for the beta phase and equal to 0 for the alpha phase, and this varies smoothly. Okay, and the phase composition variables in KKS model, as you have seen that there is a phase, these additional composition variables that you use are C alpha R and C beta R. And the local composition CR is an interpolation between the phase composition variables. Okay, and all other physical variables such as lattice misfit, that is a misfit strain, and the elastic constants are interpolated by functions of phi. So in this case, I don't do that. In this case, elastic constants are basically not functions of phi. I'll come to that. But in homogeneous case, everything else is a function of the phi, the phase field variable. That distinguishes between alpha and beta. Yeah, so once it is done, what we do is we write the energetics. So in the energetics, you have the total energy, which has this chemical part and the elastic part. And the chemical part, as you can see, is a volume integral of two terms. One is the bulk part, and another is the gradient energy part. And this gradient energy part, this kappa is kappa itself is a tensor. In fact, kappa is a second rank tensor. So if you want to face, for example, if you want to introduce tetragonal type of anisotropy, you can do that with kappa itself. So, however, if you want to go to higher order anisotropy, then you can cubic anisotropy. You have to go to fourth order terms. Guru is there. Guru has developed sixth order, means he has extended to sixth order to introduce hexagonal anisotropy. So however, so here in our model, what we have used, since it's a cubic crystal, we are assuming cubic crystals, alpha and beta both are cubic. Therefore, for cubic crystals, this is a second rank tensor. So this second rank tensor becomes basically a constant times the identity matrix, right? So this is the for cubic crystals. So this is what we are using. So that is one value of kappa, and since there are only two phases, I have only one value of kappa. I'll tell you how this kappa is derived in KKS model. It comes from the equilibrium phase field profile. So the bulk chemical energy, free energy density, if you n component n phases, as you can see, I varies from 1 to n, small n, and phi can vary from 1 to capital N. So we are looking at we are currently extending into multi-phase. Currently, it is the model can be done for 2 components and 2 phases. We have already done the multi-component, but we haven't released it. We are testing further. So if you look at the bulk chemical free energy density, then it is again, as you have seen previously, it's an interpolation of F alpha and F beta with a barrier energy, that is so which is approximated as a double well. If you remember in morning, Abhik was talking about multiple obstacles and double obstacle for 2 phases. So here, instead of obstacle potential, we are using a double well potential, and we use an interpolation function of this type. And if you plot this, you can see it's varies very smoothly between 0 and 1 with these properties. H0 and H1 are 0, and for 0 phi between 0 and 1, H phi also varies between 0 and 1. Another important thing is the H prime at 0 and 1 are also 0. Okay, so as I told you, potential barrier between the 2 phases is given by a double well potential, where omega gives the barrier height. Omega gives the barrier height, and this is phi squared 1 minus phi squared, which has this form, right? Which has this. This is one well, and this is the other well. So that's why it's double well. Now comes the elastic energy density. Elastic energy density is very simple. It is basically sigma times epsilon elastic, right? It's a elastic strain times stress is the elastic energy. And if you see, elastic strain is a function of R, sigma is a function of R. So at each point, this is the elastic energy density. If I integrate it, then I get the total elastic energy over the volume, right? And if I write sigma, if I use, since I am talking about elastic energy, so I use sigma equals to C epsilon. That is the Hooke's law, right? So sigma equals to C epsilon. So that if I use that, and remember this is epsilon elastic, so this is basically C. C is a fourth rank tensor, so I am putting a double dot epsilon total minus epsilon. This is the misfit strain. This is the stress-free strain or stress-free transformation strain. So if I want to use position dependent elastic constant elastic modulus tensor, then this is how I can write that CR. C is also a function of R, that's position, and I can write it in two parts. One is the homogeneous part, one is the heterogeneous part, and heterogeneous part again I can make it a function of phi. However, here in this model, the solver that we are using has, even with homogeneous modulus approximation, this is something that I can tell you, you can basically see most of the first order effects can be basically studied just using homogeneous modulus approximation. You don't require inhomogeneous elastic inhomogeneity for this. One of the major first order effects in precipitate growth and coarsening, that is particularly shape change with size. And so here we are using CR equal to C naught. And you have eigenstrain field, that is also a very interesting field. Means in traditional phase field models, eigenstrain field is often related to composition, right? Means composition modulations, for example, Pigard's law you often use. Here we actually slave it to the phase field itself. And if you look at the typical form of this eigenstrain, then you see that it can basically be, so this TM1, for example, is epsilon 2 star by epsilon 1 star. So epsilon star is the magnitude of the strain for of the eigenstrain. So I can use, like, the TM1 and TM2. These are basically tetragonalities, and these tetragonalities can introduce anisotropy in eigenstrain. But in our first example, a few examples, we will use dilatational eigenstrain. So I'll go a little bit into what you might mean by dilatational misfit. By the way, dilatation can be positive, dilatation can be, means it can be contraction also, right? So for example, here if you can see, so first of all, we are looking at coherent interfaces. Coherent interfaces means this is all from Porter and Stilling, very standard textbook. So lattice planes and directions are continuous across the coherent interface. And what you see, so I'll tell you, this is basically what we are looking at is, I have the lattice parameter of the matrix, which is alpha, and lattice parameter of the precipitate, which is beta. Now to basically keep the interfaces coherent, there will be some strain associated with the interfaces, right? So that is the coherency strain, and that is related to this epsilon star, as I told you, is the lattice parameter mismatch, a beta minus a alpha by a alpha. And since you are using the dilatational misfit, you can use Kronecker delta. Kronecker delta is nothing but I, the identity matrix, times some psi phi. Psi is a function of phi. Psi phi can be phi, it can be h phi. I think we can use both a phi and h phi in our code. However, you can also use some tan h function or whatever function you feel like. Right, so you can use. The only thing is, you have to, that function should make sense, that it ultimately tells you that this is how the misfit strain is distributed between the alpha phase and beta phase. That's the idea. And as you can see, dilatational misfit is, you have a circle, alpha, say I am thinking of a just don't think of this as a circle, you think of this as a domain, alpha domain and beta domain. Beta has a larger lattice parameter say than alpha. Then you have a dilatational misfit. It can be also have smaller, but see, the circle remains circle. The idea is that the circle remains circle. Circle does not change shape. On the other hand, alpha beta, if you look at this type of this picture, you see alpha is circular, it has a circular symmetry, beta has become elliptical. So you have something called anisotropic misfit. So you have different misfits along x and y, right? So that both are possible and both can be used. And that is one of the biggest advantages in cubic crystals. If I put eigenstrain as a function of composition, I have to only use dilatational eigenstrain. However, since eigenstrain is a function of phi, okay, and since eigenstrain is a function of phi, because eigenstrain is also a property, right? So it has to follow the underlying cubics, and it's a second rank tensor, so it has to be dilatational if I slave it to composition. However, if I slave it to phi, I can now use any type of tetragonality. I can make it as anisotropic as possible. So another thing is elastic anisotropy. Please excuse this thing. I borrowed it from my student's thesis, so I did not draw it by myself. So what I wanted to tell is this this elastic anisotropy parameter, this Zener anisotropy parameter is 2C4 C1 minus C1 2. If you look at this, you see that there are cusps. So if AZ is positive, if AZ is positive, this is for equal to 3, you see there are cusps along the 1, 0 directions. In 3D, actually, there are some very nice 3D pictures also Tushar and Shomo have done. So you can see that these cusps are like, along all the 6 cubic directions. So you can, however, as soon as Z is less than 1, you will see that the cusps are now along the 1, 1. So in 2D, it is 1, 1 direction, but in 3D, the picture looks very nice. You will see this along the 1, 1, 1 directions, right? The elastic energy reduces. So another case is approximately. So here I have done approximately 1. If it is exactly 1, it is perfect circle. If it is approximately 1, it is near, means it's circular, right? So there is no cusp, nothing. So and you see a very circular symmetry in the elastic energy. As a function of, remember, this is a polar plot. So this is along the this is a polar plot, right? So this is along different directions. So you can see along these directions there are cusps when AZ is less than 1. So evolution equations have been already discussed. So for KKS model in the previous talk, Mohan has talked about that. So these are the two evolution equations that we solve. One is the Allen-Kahn equation. As you can see here, only thing that has come is the elastic driving force, right? So the additional thing that has come here is elastic driving force, and mine is much less complex than the one that was used earlier, right? So it is like a very simple equation. And then you have also this diffusion equation, which is basically, if you see, it is just grad dot m grad mu tilde, and mu tilde is the diffusion potential. And this diffusion potential has been explained by Avik, so I don't have to explain. So you are looking more at the slope rather than at the intercepts. And for equal, and we always so if you look at the sharp interface Stefan condition, so basically we are always looking at the alpha beta interface to be at equilibrium. So we have to solve the this equality of diffusion potentials, and you have to together with the C phi interpolation that you do for relating C alpha and C beta to get the C alpha and C beta at each step in the evolution. And we solve it using a semi-implicit Fourier spectral method, assuming, so as soon as I use Fourier, it is implied that we are using periodic boundary conditions. So these solvers become very efficient when we use, efficient means fast, okay, when we use periodic boundary conditions, because you can use fast Fourier transforms, right? So that's why we solve all these the governing equations in Fourier space. But you can also solve using finite difference, and we are trying to develop a routine for that. And the second, and we also have to solve, so because I require the elastic driving force, I require to solve the mechanical equilibrium equation, which is grad dot sigma equal to 0. And what happened? With this jump conditions and this continuity in displacements, and it gives the, so, and since we are again using Fourier, we are using Fourier spectral method where the displacement is periodic, right? And it displays there is a homogeneous part of the of strain and the heterogeneous strain, right? So we use means basically we use the displacement has like two parts. I don't know what is happening. So as you can see, so the displacement is periodic, and as a result, we can use Khachaturian's theory. And this uh, you may look at Khachaturian's theory, but I'll tell you what we do. So what we do means it is there in the manual, so you can basically see that if you have this equation del 2 u c I j k l del 2 u del xj del x del rj del rl equals to c I j k l epsilon k l 0 r. The best thing that you can do is basically, as you know, Green's function method. So, the Green's function method, in general, either you use delta function or you use Fourier transforms, right? Here what we will do is, and since u is periodic, so we can directly use Fourier transform, and if we use that, then we find the term Cijkl njnl, which is basically my gik, that G tensor that you can see. So this G, and this is J is basically the complex number. J is root minus 1. Okay, so it's very simple to do, and in the manual it is done. So once you do that, that means what happens is you get, and since you are using homogeneous modulus, you get the solution in one step. Once you get the solution in Fourier space, you just inverse Fourier transform and take it to real space. And once you get that real space displacement solution, you can compute the total strain, and then you can subtract the eigenstrain and get the elastic strain. And once you get elastic strain, you can basically multiply with C and get the stress. And elastic driving force is proportional to the negative of stress, right? I think negative stress, yeah. So then basically you include it, the del F elastic del phi in the Allen-Kahn equation and go on solving. Okay, so one of the things that why CUDA, you can actually do it using FFTW itself on a serial code, but why CUDA? Because we wanted to go for larger systems, and also we wanted to go fast. One of the major things was fast, and now since we want to go to larger systems, we are finding a bottleneck. So we want to now implement CUDA plus MPI, so that MPI, we look at big simulations and we see, oh, wow, these are very, very large. We can't go so large because GPU cards still have limitations. But they are fast. They are definitely fast. We can go to 3 dimensions. That is one thing. Previously, that also, if we go to 3 dimensions in a serial code, it will run for 15 days, okay, with the same size. So now it runs in 24 hours. So that's the idea of using CUDA. Okay, so we use this NVIDIA CUDA toolkit, which is available with any GPU card. See, if you have a gaming laptop or gaming desktop, that also will have, say, for example, a GeForce card, or a RTX card or a GTX card. You will basically have, for example, Shourav runs it on his laptop, which has some GTX card, right, Shourav?
Yes, I run it on a GTX 1650.
Yeah, GTX 1650. So any card with some CUDA cores will run. Only thing is, remember, in NSM you can run much larger systems. You can because you have like state-of-the-art GPU cards which are meant for GPU computation. GeForce cards will have lots of other things, other usages. So that is why you may not be able to have so many CUDA cores, and your solutions may be very slow. However, you can run it if you have a NVIDIA card. Okay, so this is a very important thing. It has to be a CUDA capable NVIDIA card. Remember, this is something that you have to check. when you buy your desktop or something. And then you can basically, and once you have done that, then you, and if you want to see whether NVIDIA CUDA toolkit is installed, you just have to see whether this compiler NVCC is there. Okay, so if you have NVCC, then you will see, say for example, when Saurabh runs it or I run it, we get all this version, right? So NVIDIA CUDA compiler driver and built on this date and whatever. And then you can see that what is the version. So this is CUDA 11.5, right? So it's a release 11.5. 10.0 onwards, I think even 9.2 onwards it will work, but we have tested 10.0 onwards. So we have verified that it works with CUDA toolkit, which is 10.0 and above. Okay, so, and another thing, this CUDA toolkit is available for free from NVIDIA website. It is also available as a repository in Ubuntu, and I don't know whether it is there in Debian. Ubuntu will be there. In Arch Deluxe also, I think Saurabh was telling me it's there. So CUDA toolkit, or you can directly install it from NVIDIA website. It's free, and you can easily get it. So once it is done, first thing is you have to, so if you want to run the code that I will demonstrate, you require to run this command, okay, NVIDIA SMI. So now this is not from the GPU that we use in NSM. This is from Saurabh's laptop. Okay, that is a screenshot. So if you see that there is a driver version, there is a CUDA version, and if you look at it's a GeForce card, you can see that, and the temperature also will be shown, and how much of memory is available. So all these things will be given. Okay, so this is something quite good. So you can run it on a good workstation also with the NVIDIA GPU card. So, and another important thing that I will tell you, that while compiling, we have used some specific architecture specific flags. Okay, so there are different types of CUDA cards. Okay, for example, Fermi, Kepler is like K80, K40 and all, and then you have this Pascal cards, and then Volta, and currently I think this A80 and new cards are coming. So for specific architecture, so we use, for say for example, SM35 for Kepler, and SM7 I think SM70 for Volta cards. You can use, you have to find this out. So we have pasted it here, and I hope that what we will do is we will also paste this in the manual, so that you can find out which card you should run. Because if you don't use the architecture flags, I have also seen that it is not optimized for your architecture and it may run slower. Okay, another very important thing in our package is that we use NVIDIA's CUB library. CUB is an open source library, and it's a very beautiful library because it can handle all these different, this maximum, minimum, summation, and all this stuff. It can do very nicely. Okay, it's a CUB is a very powerful library in NVIDIA, and CUB works on that particular GPU, and CUB does what in C, for example, typically say stdlib.h will do. So CUB that way has a lot of functionality, and it is important that that you have the appropriate CUB library. Okay, so it comes with compatible CUB libraries for all these CUDA 11.2, 11.4, 11.5. If you are using CUDA 11 less than 11.2, then you may have to basically get the CUB library separately. Okay, so, and it's possible, but you may also you can check what is the CUB library that is there in the KKS CuFFT directory. Not good. Okay, so the implementation, in why CUDA implementation becomes faster? This is because if you see in NSM, you have a lot of so one the Tesla Volta cards, for example, have a huge number of CUDA codes. Now, when you have that, you think of in CUDA, the way we implement the code is very simple. You have a grid. Okay, say this is the grid dimensions. These are the grid dimensions. The grids are now divided into blocks. Now take one block. Now this is the block. In that block, there is also the subdivisions that are called threads. Threads are the smallest things. Okay, so threads are basically the smallest units in our implementation. Now each thread, so as soon as we basically execute a CuFFT code, or you want to copy some or do some operation, multiplication or addition, what happens is each thread appropriately will take that particular thing from the global memory, that is like 32 GB for or 16 GB for the Tesla card, and it will keep it in the thread. And that this thread, although we are not using shared memory, mind that. So once it is there in the thread, so all these threads are in the block and the block is in the grid. So the entire thing is immediately spawned across so many threads. You understand? So it is using all these threads to do the calculation at an instance. So that is the idea, because you have very large number of cores. Okay, in this GPU cards, these advanced GPU cards. So that is the idea. And once you have that, each thread can be accessed using an index. Remember, the threads have very less memory by itself, but the thread also contains very little information. It's like one data point. That's all. So that is what it is. So for that one data point, whatever memory is required, that is there. And that is what is required for the, so and now for that data point, it is doing all these operations. So you have the IJK, and this IJK is given this way. So as you can see that this is like block ID, and this is the thread ID. And so this is how, so block ID is basically the index of a block in the grid, and thread ID is in the index of a thread in the thread block. So if you want to develop further, for example, that this is standard thing that we generally use. Okay, obviously you can look at that, check how to optimize this number of threads. Saurav has done a lot of optimization on his GPU as well as on the NSM GPUs. So we have, I think, now a very good distribution, means we know the most optimum number of threads that we should use. And if you see, apart from stdio, stdlib, and math, you use this CUDA.h, CuFFT.h, and you can use CuComplex.h and CuP.h. These are the libraries that come from CUDA. Okay, so this is the idea. So there are some model-specific inputs in the library. I will come to that. I'll demonstrate. So model-specific inputs, there is one thing called elastint, which has to be made 1, toggle to 1. You cannot toggle it to 0. If you do 0, then it disables elasticity solver. If you want to use elasticity solver, then you have to toggle it to 1. And since we are having one interface, because the two-phase system with one type of interface, alpha beta, we have only one relaxation coefficient parameter. However, if you have say alpha beta gamma, then you require an relaxation coefficient for alpha beta, alpha gamma, and beta gamma. And C0, again, C0 for one value for a binary alloy, but for a multi-component alloy, you can have several C0s, which will C0s for each component. So this will be again a tuple, and this will indicate the overall supersaturation. And these are the F0 alpha and F0 beta, the coefficients of the parabolic free energies that we are using, that are basically curvatures of alpha and beta at the equilibrium compositions. And we use this alpha bar, which is a constant in the KKS model, associated with this diffuse interface. This is a constant that has been evaluated. And this lambda alpha beta, again, I have only one interface fit because I am looking at only one type of interface, alpha beta. So what we typically input, we can input kappa and omega, as Abhik also told in the morning, but here we input the interfacial energy and interfacial weight, and then we get the potential barrier height omega and the gradient energy coefficient kappa alpha beta. So this also was illustrated previously by Mohan. Another thing that we haven't mentioned here, I haven't mentioned here, yeah. So M also, we make sure that L by M ratio is such that you have diffusion control group. Okay, so that's the thing. And typically the formula that is used by Mohan is the same formula that we use for finding the appropriate L value that we should use, so that we ensure diffusion control group. These I will anyway show that in the GUI. So one important thing that is there in our code. So these are the very specific parameters, like eigenstrain. You have for each phase, 0 is the phase alpha, 1 is phase beta, and you have these eigenstrength values. So you can see epsilon xx, y, z, z, y, z, x, z, and x, y. Because it's a symmetric tensor, so you don't have to give z, y, z, x, and y, x. And you have, currently we have white isotropic. For isotropic, you don't require C44. I think there is a mistake. You don't require C44. You just require phase and C1 and C11 and C12. For white cubic, actually this is not there in the as a part of the input.in. I think this has come here by mistake. Print typographical mistake. Sorry for that. So white cubic, you require these three independent elastic constants: C11, C12, and C44. And see, for example, we are using for 0 and 1, we are using the same, as I told you, homogeneous modulus approximation. However, if you see 2400 by 700, we are using some approximately like, if you see 2C44, this is C44, right? 2C44 is 2400 by 700, which is something like 3.1 or so as the Zener anisotropy parameter. You can also, if you have tetragonal, you require 1, 1, 1, 2, 1, 3, and 3, 3, 4, 4, 6, 6. 3, 4, 4, yeah, it's a fourth rank. Yeah, so you require 6 independent elastic constants. Yeah. So, and as has been told that we currently use VTK files, and VTK supports both ASCII, means the file writer supports both ASCII and binary file writing, and these are some, and there is now we have added this restart, so we can basically stop the simulation and start again. Okay, so, and this is say some typical value of supersaturation, alpha value, and lambda value. Alpha is 2.94. I don't know whether we use 3. I'll check this. So there are, this is another very important thing that I want to tell you. There is a filling.in as has been demonstrated, and already these 3 functions are there: fill cylinder, fill sphere, and these functions are fill cylinder, fill sphere, and there is also a fill cube. But we also use, it's already there in the our filling.in, fill cylinder random. Okay, where we basically generate this. So it is basically, one represents the phase, so it represents the phase identifier. This is the precipitate radius, and this is the volume fraction. And we use a shielding distance. For example, if I have a precipitate like this, so we take a center to surface shielding distance. Say if I tell 2, so it is like if the radius is r, then I am taking 2r as a shielding distance. That means no particle will come within this 2r. You may have 0 shielding distance also, does not matter, but we are using, but here typically we have used 2, but you can use, you can specify your shielding distance. You can have overlapping particles also. And in 3D we use this field sphere random, right? So you have phase, again the phase identifier, the precipitate radius, the volume fraction, and shielding distance. So you are ready to run the solver. So I will show you how to run, and then we can basically see the VTK files. So as you can see, what is the effect of elastic anisotropy? I can show you in a movie here. See, Az equal to 1, you see it's circular. In Az greater than 1, you see it has become cuboidal. And here, what is happening? It has become a diamond-like shape because it has the low energy. So if you look at the low energy facets are along 1, 1 directions. So it is for Az less than 1. So these are some few large scale simulations. Once I finish, I show these large scale simulations to basically excite you a little bit. Then you can, I can do the hands-on. So large scale simulations. So for example, this is for a 512 cube system, and let me run it. How do I run this? As you can see, this is done. This is with elasticity tandem, and as you can see that all these particles which were initially spheres, they turn into they were initially cuboidal, then they become plates, and you can see all these different plates that are there. It takes this 512 cube system previously in serial, means in a fully serial code. It would have taken a large number of days. However, now it takes 24 hours of computing time on a single Tesla V100 GPU card. and this is for anisotropic. So in this case, what we have done is so this where is it? Yeah, this is for anisotropic misfit. So what we done is we have kept epsilon x equal to 0, and if you see this is the x direction, and you will see that these guys are elongating like rods along the x direction, the low misfit direction. This again on a 512 cube system. So now we will do some demonstration. Obviously not on a 512 cube system because it will take 24 hours. So if you have any question till now, you please ask me. If none,
with respect to some from Harris Daniel.
okay. Hello.
Harris, you can ask your questions.
Yeah, I felt that while I faced some issues while installing OpenCL and CUDA, so I thought it would be beneficial if you provide us with some installation instructions in your GitHub page.
Absolutely, I'll do that. Well, OpenCL, I think Mohan can help you, and I can help you with CUDA. The only thing is you require to have an NVIDIA card, CUDA capable card, okay, which can be G4 GTX or RTX. You should have a card. So
Okay.
if you have that card, then it is very easy. And where are you trying to install? Please understand, we have tested this code on Linux environment, so not on Windows or.
No. I'm talking about a Linux environment and
Okay.
Ubuntu Mission with NVIDIA
Okay,
card.
so absolutely, we will help you with the way to install the CUDA. Yeah.
Thank you so much.
So I'll go to the. So first, let me close this now. Then I'll show you some of the simulations. Close this thing. So if you want to, basically, if you want to say, I can show you how to run the make file also. So if you look at the make file, if you see that we use like so we use SM70. So this is a very specific, flag that we use for Tesla Volta machine. So I will tell you. So why do we use that? Because we looked at NVIDIA SMI, and we see that this is CUDA 11.2, and you see this is V100 PCI card, and the temperature is very high because somebody is running. It's not really very high because if you see, it is just consuming 76 watt out of 250 watts. So and if you look at that, so this is something I think the question that you have is once you install, see, don't install NVIDIA driver separately. I have found that Saurabh, am I correct that we can directly install the CUDA toolkit? It takes everything.
Yeah, it will include everything.
It exactly. So it will. So do not install separately. Then if there is a version mismatch for the NVIDIA driver and the CUDA version, then there will be a big problem. Okay. So just install the CUDA toolkit. It will come with its own baggage, and it will install whichever driver is appropriate. Because you may install a very advanced driver, which is say very good for say some other purpose, maybe visualization. But what will happen is that driver version may not be compatible with the CUDA toolkit, so you may face difficulties. Okay, so now once you have that, then you can just run make. Okay, so make basically gives you this executable name. Make means we are using MicroSim KKS CuFFT. So I go back. Now I go to the MicroSim folder, and I'll just show you. So please try to understand. So I'll show you some of the existing in files I can import, and I can again save. Okay, so if you have any question, please let me know. You can go on asking questions while I demonstrate. So one of the things is this. This is one problem that I get. That's why I cannot, use. Yeah. So first thing, this animation is there, so it takes some time. Then the GPU CUDA model. Choose this.
This code considers double precision.
Yes, yes. See, that is what I wanted to tell you. Our code is fully double precision. That's why it is very good in Volta and Pascal type of cards, or even Kepler cards. So that is one very important good question, that you will have these G4 GTX cards and these RTX cards, and some of these, see, all of these cards will also support double precision. Only thing is double precision calculations will be much slower than floating point. Okay, so you will be still able to run the code, but only thing, it will be significantly, means much slower than a typical Volta or Kepler card. But you can still run it. There is no problem. I'll just show first. Okay, I should show it without lassity.
So how will be the speed compared to equivalent CPU code?
So I will tell you, 512 cube type of code we have tried to run previously, and we have found that it is in the CPU. What happens with normal FFTW, even with OpenMP, it really literally crawls. So it goes like a huge, because you understand, as I told you, this grid. See FFT is what? FFT is a summation, right? It's a summation operation. Now FFTW does it. However, what happens is, the way it does it, because you do not have so many cores available, right? In a CPU, it is like how many? 16 cores. You may have 32 cores. You don't have more than that. If you look at a typical OpenMP code, you have only a very few number of cores available. On the other hand, if you look at, there is something called device query. You will see that the number of cores in CUDA cores in Tesla Volta is like some more than 3,500. So huge number of cores. Now you can see how fast, when I spread this matrix and do the Fourier transform, how fast the Fourier transform is executed. Because one of the major times, if you look at the profiling, you can do NVProf, by the way, on the executable, and you can find out how much time is spent in each part of the code. You will see that there is a significant time spent in this Fourier transforms, and these Fourier transforms are so fast that sometimes the Fourier means they become unbelievably fast when you use this CuFFT library compared to FFTW. This is just because the number of cores have become very large in GPU. You don't have so many cores in your CPU. As simple as that. If you would have got the same number of cores, maybe it would have not have been so slow. Otherwise, it becomes like 32 is to 4,000. You understand the ratio. So that is how, and it scales like that, So it goes on, and it does not give you anything for quite some time. Without lassity. 2D single no elasticity. Yeah, first one is this. So I open this, then I open this. So I am importing the input.in. Okay. Now, if you look at that, you see the simulation geometry. You can see that it is a 2-dimension. It is 256 by 256, dimensions 2. Mesh set is not highlighted. If you look at the discretization, 1, 1, delta z does not make any sense here, and delta t is 0.1. Now, go to phase. So as I told you that currently our code has 2 phases and 2 components. So we are using 2 phases and 2 components, and phase name we are using alpha and beta. And here we have is LZN, whatever. You can use C1, C2, whichever you want. And then you have iterations. So you have these time steps. I have used n smooth equal to 0, but you should use some n smooth. Okay, so if you want n smooth equal to 4 or 10, maybe you can use. N smooth equal to 0 gives you a very rough circle. So and then this is the save at time, and as you can see there is a restart flag, and if you want to give, you have to, since you can restart the simulation, you have to give the restart flag to be 1, and then you have to give the start time. See, if you give 1, immediately start time gets highlighted, right? So that's the thing. Now you have the material parameters. So alpha phase, we are using diagonal diffusivities. However, again, you can use, so that is one thing that we are going to release very quickly. This thermodynamic data and kinetic databases, all these things you can integrate and put. However, diffusivity, be very careful. Most of the diffusivity databases that come with the commercial software are wrong. Okay, so they have a lot of problems, because multi-component diffusion, most of them extrapolate, and this extrapolation gives you very wrong results. So be very careful with the diffusivities. So it is often better, to use diffusivities only the diagonal components, ignore all the non-diagonal components. Because there can be, the orders may be more or less okay in the case of diffusivities. So eigenstrain. So this is the eigenstrain. As you can see, I have a dilatational eigenstrain. So in this case, we are giving elastin equal to 0. So eigenstrain will not, whatever eigenstrain I give, it does not matter. Now, if I use cubic, you see, I require to give a tuple of 3 elements, right? 2700 is C11, this is C12, and this is C44. In fact, you can check one thing, although we also check that. So that positive definiteness of the elastic constants also you can check. Okay, so that you cannot just give random values and think that the code will work. Okay, if the elastic constants are not positive definite, then there might be actually there will be problems, and you will get wrong simulation results. And this is again, this is the interfacial energy 0.8 we are using currently, and since we are using non-dimensional values, we have taken R1, V1 and stuff, and gamma is the interfacial energy between alpha and beta, and now if you have multiple phases, as you know, we have to again put this also as a tuple. Boundary conditions for phi PBC, so you can see all are PBC, and for C also it's PBC. See, mu and T we are not using, so mu and T are redundant for us, but C and phi are PBC. And then we use a domain filling in this case, so we can import the shape, and I tell you what is the domain filling function. So if I go to filling.in, open, now you can see that it is for phase 1. Phase we are taking a 128 and 128 as center, 0 0 x z start z end, and this radius is 24. You can take also a smaller radius, and not a problem. But again, as Apik has pointed out in the previous talk, that you be careful that at least 8 to 10 grid points, maybe 10 grid points is a better idea. 10 grid points should be there at the interface. Okay, so whatever interfacial width you choose, whatever values you choose, make sure that you have 10 grid points at the interface. And one second, is there anything else I have to do? Yeah, we have to select the model here, KKS GPU model, that is select. Okay, and once we do that, we have that binary, and then this is the track progress. Okay, so it gives some maximum minimum values, and then relax coefficient. I am again using one relax coefficient here because, and then this alpha is a specific parameter that is related to the interface, the diffuse proportion of the interface. We are taking between 0.05 and 0.95, I think, and therefore the alpha comes out to be 2.94, and we are choosing an interfacial width of 8.0. And C0, Okay, so here, for example, I think we are using the 4.0, 4.0, and here, for example, we are using 0.5 and 0.8 as the equilibrium compositions of the two phases, alpha and beta. And F0 is the curvature value. Okay, and then so all these things are done. Yeah, 0.5 and 0.8, right? So, and we have adding no noise, but here you can see elasticity is 0. As you can see, elasticity is 0. Now you can basically generate files. So I'm just overwriting the files in the same directory. So it creates the files, and then I can run. I click on run. Something should happen. You can very slow.
Executable file should be there, I think.
Ah, no, it's there. It's there. It's there. It is running. Yeah, it runs. You can see, na? Actually, what happens is, see, in a workstation, no, genome terminal works, but for us now, extern works. So because we installed it as a server, so we had very bare minimum GUI in the on the node that we are using. So that's why I had to use an extern and I had to reroute it to extern. So it works actually. So as you can see, it runs, and now I can show you. Okay, how it runs, we can show you. Okay, so let's say, for example, then just gone somewhere. Ish, very sorry for this. It is taking a lot of time. Apply. So as you can see, the particle is growing, and right, and the particle is growing. The circle is growing like a circle because there is no elasticity, and also the elasticity is not. See, even with elasticity, it can grow as a circle if the AZ is isotropic, right? And the misfit strain is dilatational. Remember, both have to be there. Misfit strain has to be dilatational, and AZ equal to 1. That is the elastic constants have to be isotropic. So in that case, it will just grow like a circle. Only thing is, since elastic energy is added, it will grow at a slower rate. Okay, so similarly, now I can do with so yeah, it is running. See, so I just Control C and stop it. Okay, so similarly, so I can, so if I want to do multi-particle, I'll just give, because for the sake of time, maybe Abhik, shall I go for multi-particle directly?
You can do that.
Okay. It is continuously. I have pressed run too many times.
Yes, exactly. You have run twice. Run.
So it went on running.
So you can close that terminal. That is all.
Yes, I'll do that. See, it does not want to stop.
Right. So
So,
I think you have pressed it 3 times.
one second, I'll have to check. No, I have to close this terminal then. Yeah, so I don't want to do that. So I think it will stop now. Yeah, it has stopped. See, there is a problem, communication problem. I am connecting through SSH, so that's why it takes some time. So I will show you one another example, and yeah. So say, for example, 3D multiple particle elastic. Okay, so I just import this file. I open it. So now you see it is basically 3-dimensional and it's 128 cubed. Okay, so it's a small system, so that's why we can run it, and we can in few minutes we will get a lot of data. So, and we are using delta x, delta y, delta t is 1, and delta t is 0.1, and delta x, delta y, delta z is 1. Sorry, and again the phase information is same. Iterations again you can use like 10 iterations for something, and then again the alpha phase and beta phase we are using diagonal diffusivities, and these are the, now if you see I have to give epsilon xx, epsilon yy, so I am assuming a dilatational eigenstrength, so that means I have to give epsilon xx equal to epsilon yy equals to epsilon zz, and all the other parameters I have taken as 0. Okay, in the given reference frame. Okay, we have my reference frame is aligned with the Cartesian coordinates, right? If I want to rotate it, obviously, as you know, the transformation rule will be applied for all these tensors, and we have to then accordingly give the or we can give the same coefficients, same things, but it will be transformed. But it is not yet implemented in this model. We can do that. So and we have these 3 elastic constants. We have gamma, R, V, and then boundary conditions are same PBC, right? It's FFT means we are using PBC. However, I will tell you one thing. You can also use Neumann boundary conditions on both sides. They're not a problem. If I use a sign, so we will introduce all of this, right? So we can do sine and cosine Fourier transform, and I'll put those things. Yeah. So now this is something that I wanted to tell you, that when I have these random particles, it is a feature that will come. I am sure it is not yet included in the graphical user interface, but it is already there. Means it's already there in our code. So if you look at that, so this is sphere. So we are generating randomly the spheres. So these are of so the volume fraction is 0.15, and we are again using a shielding distance of 2, and the radius is 12, and I think we give a perturbation, right, on the size, so slightly, so there is like 1% or 2% type of perturbation that we give on the radius. Okay, so this is how we create this random spheres. Once all of us converge on how to put these things for random filling, then I think it will be included in the graphical code. So again, I have to use this, and then I have to go to this. This is fine. This is fine. So here we are using x0 is 10. Then elasticity is 1, as you can see, and the values are 0.5 and 0.8. Go next. And we generate the files. Okay. Now I just run once. Yeah. It has to open that external thing. That's all. That's double click or what? I am not understanding. See, one thing you can do, once you once you generate the we have 44 particles.
So this will take a bit of time, so we can skip ahead to the visualization, I think.
It will take how much time? 5 minutes, 10 minutes?
Yeah, the filling
it will take 5 minutes, huh?
Which is why I restart directly from the filled file. So I save it at time equal to 0, and then I read that and start.
Oh. But it is just taking this plan thing is taking time, is it?
No. So what it does here is it generates random spheres, and then it checks if.
So that filling itself takes time. Yes.
Yes.
I get the point. Yeah. So yeah. So this is something that we have to take care of. That filling operation takes some time, but not much time. It does not take too much time. Yeah. I'll directly go to visualization. Means how it looks like. I'll show you. It takes more than 5 minutes.
I think like it's better if we go to the visualization.
Oh.
I don't know exactly how much time it will take since other codes are running on the GPU.
That is also a problem. Yeah. So I have to delete this one. No? Okay. And then I have to use volume, and then I have to run it. No, but it should go to the fast thing. No? Yeah. So it has all this. Yeah. Okay, this is one issue that I have to now think of. Actually, filling can be basically separated out, and then we can just read it. So basically,
Yeah,
I
so
can restart. Yeah.
this is a feature which will be included in all of our models, where
Yes.
the initial file can be created separately as well as a feature, and that can be just read in the solver. Particularly for National Supercomputing Mission usage, if the filling operation takes too much time, then we are losing out on computing time, which is costly. So the filling operation we will be separating out in the future as a separate. I mean, the feature is already there.
It
If
is
you
already there. Restart is already there.
because restart is already there. So typically we can, as a workflow, have the filling operation separately done and read in the solvers. So this can be integrated.
Yes. So this is something that also seems quite interesting. So you can see that. But once the filling operation is done, I wanted to. Means once it is done. So I'll just take 1 more minute. Is it okay, Abhi?
Yeah, until 4 you finish.
Okay. So that I can, I can just use a restart thing and tell them, see, without filling, it actually starts running. This filling is becoming a bit of a problem. So Saurabh, tell me what times shall I start? 1000 something?
No, that just 0. It will work. Just 0. Yeah. It starts from 0 with 5. That's it.
Yes, right. Everything is there.
So you have to generate the in file first.
Oh.
Now it will throw up an error because it's already running.
No.
Yeah, you have to generate the in file because it's the older in file itself.
No, so that output name should match. That is the issue. So you can change the output name and it will work.
No, I have to generate the in file. No? Otherwise, restart. How will it know that it is restarted?
That is also, yes.
And output name has to be same. Output name has to be same what he has saved.
Which you can just remove the dot out and change the first letter to capital. So capital O out.
So it is not able to see. Yes. So I have to do that.
No, for this you don't need to generate in file. It's already generated. Don't worry.
Anyway, better to be safe. It is good, better that I run it with non-GUI, but yeah, both are very important. The GUI looks very nice. It's really, really beautiful. So yes,
Yeah.
see, it has started. So yeah, you see, it goes 25 steps immediately. So that's the point. So it does that. Okay, so you can see that it has already gone to some 125 steps, 1,000 steps. Again, here be very careful. One of the important concerns that I found out. See again, if you are running, you please note to make sure that your DT, again, it's a semi-implicit method. It's not a fully implicit method. It's not like the open form method that Abhi discussed. So any DT will not work. Please try to understand. Okay, so this is another thing that you may become unstable. Yes. I'm stopping it now. And
Yes, that's what. So we
yeah,
can now.
now, if anyone has any question, so there are several things we did. In fact, I'll show you one very interesting simulation we did that was without elasticity, 3D. Looks nice. We like the patterns actually. Beginners. Oops, I haven't given volume. Why did I do this?
No, you have to click on the eye.
I clicked. Then I have to give the volume, no?
No, solid color. Check. Exactly.
Volume. See, it coalesces, coalesces, does everything. It's remember that when you go to small simulations, you will see more coalescence also. If you go to very small scale simulations, coalescence may dominate because means that I don't know why it is happening, but it seems like that at a very small scale when you go, coalescence often, maybe this is because of the shielding distance. So this is, but both happens, coalescence and coarsening. But if you go to larger and larger systems, you will see coalescence is very less. It's mostly coarsening that happens. So I would, yeah. So if you have any questions regarding the elastic stress effects, or I would be happy to answer.
Shashta, this is Ram here.
Yes.
Hey, in these precipitate evolution calculation, I mean, these transformation, elastic transformation calculations, martensite like athermal transformations, does it come in?
Yes, we can do that. We don't require to solve diffusion equation then, and we just have to put the eigenstrengths appropriately. So we can absolutely do that. So it's actually pretty easy with this code, athermal transformations. You see, I just require to remove the, means not remove, comment out the Kahn-Hilliard equation, and we can, only thing is I have to put as many variants, as many phase fields.
Ashwata, you can put a martensite flag, and that's about it. So you put a martensite flag.
Absolutely,
if the martensite flag is there, then
yes, I'll do that. Yeah. That is like, this code is very much extensible to martensite. Thanks, Ram, for pointing this out, and that is where the transformation metrics also will help a lot. So in CIGK, so and that is already, means we can easily implement that. You understand? So that will not be a problem.
The same can be done with dynamic transformation also.
Hello, I could not hear.
Dynamic transformation also.
Benaitic transformation. You are talking about Bainites, is it?
Okay.
So Benaitic transformation means you are talking about like so Benaitic is like diffusion. It is still diffusional, right? Benaitic. Hello.
Yes. Can you
But
hear
it
me?
is multiple variants. Yes, we can do that. Hello. Gerald,
Yes,
I'm not
yes.
able to hear you.
Can you hear me now?
Yes, I can hear you. Now, can you again come with the, what exactly you asked? Can you tell?
I was just interested in knowing whether it will be able to this particular solvers will they be able to handle binary transformations?
Exactly, it can. So that's what I am trying to say. That in but Benite basically is not diffusionless. So this will be a very appropriate code, right? We just have to include the multiple variants, right? That is there in a typical Benitic structure, right?
Correct.
But it absolute, and it has diffusion already, right? So it will be a very easy extension. However, remember that Benite transformation exactly means the anisotropy, interfacial energy anisotropy will also be an important factor, which is not yet included. We will do that. So interfacial energy, elastic anisotropy is already there. But remember, inhomogeneous elastic moduli will add. But this is something that again, Gerald, I'll tell you, inhomogeneity is important for certain things like rafting and stuff. But for this type of transformations like Benite, martensite, and all, you don't require to really care about inhomogeneity. Anisotropic misfit will do it.
Okay. Thanks.
If students have any question, first of all, you can ask us. Second is you can also write to me and write to Shorav also. We will try to as much as possible. We'll try to clear your doubts. So. Yeah.
Excuse me. Yeah, this is Nathan Swaminathan. How hard would it be to actually incorporate large deformation mechanics in this model?
So that's a very good question, but it's a research problem. Already, if you look at, there are some codes like Damask, which does look at, see, mechanics, large deformation mechanics is already there. So if you look at the phase field code, we require the driving forces. So if I can extract the driving forces even by coupling with Damask code, it can be done. However, I haven't done it, and again, it's a research problem. Maybe these 2 years we will not include large deformation mechanics, but we can definitely do it as a. We are actually interested in doing it as a research.
Okay. The second question is related to what is actually used to solve the conservation of linear momentum equations.
So we use Fourier spectral method. We use Fourier spectral method. We assume, so this is basically a method that has been developed previously by Moulinet and Souquet. And in homogeneous modulus, you don't even have to go to Moulinet and Souquet. You can directly use, Khachaturian's idea. You see, it is like you think of mechanical equilibrium problem as an elastic energy minimization problem.
Okay.
And solve it. So it's exactly like, if you look at that, it is very much like finite element method.
Okay.
Isn't it?
Yep.
Or as a Green's function problem, Shashwat.
As a Green's function. Exactly. It's a Green's function.
You're using, right? Okay. One more that I wanted to ask. Okay, yeah, if I remember that, I'll ask you again.
Sure, definitely.
Sorry, can I just ask one more question, if that's okay?
Yes.
See this. I am just trying to learn some of this solution thermodynamics from some textbook in order to understand these things a little bit better.
Right.
To what extent is the effect of mechanics actually accounted for and theoretically, developed for solution models when there is actually stress effects included in the in the thermodynamics?
Okay, so this is a very nice question. First, let me tell you that in my postdoc, I have written a paper on that. But I can share that paper with you also.
That will be
But
great.
anyway, the most important thing that I wanted to tell is that in solution thermodynamics, particularly say for example regular solution models, the omega, the parameters, if you look at the way the omegas are calculated, it already takes into account these coherency strains and the strain relaxations, okay, basically between the solutes and stuff. You understand that is already included. But if you want to study it separately, you are talking about that, right? That atomic size mismatch and stuff, right?
No, so in general, whenever we have, see, for example, in none of the books that I'm actually reading right now, maybe I'm not reading the right books, I don't know. I don't see, strain or stresses appearing explicitly in the free energy functions. It's just pressure, temperature, chemical potential, or pressure, temperature, chemical potential.
So I can refer a very good book, and I think Guru will also agree, and Afik also. Kachaturian will be a very good book where you will see a lot of discussion where free energy.
What he's asking is quite generic. Essentially, the effects of stresses and can be understood by. So in a phase field formulation is very easy to understand because all you have to do is to put that stress effect in your functional.
Yeah.
So once you put it on the functional, it's going to modify the chemical part if it's a function of chemical composition. So if your stress effects, let's say, are depending on misfit stresses, which are a function of composition, they will immediately have an influence on the chemical potential, where the stress effect will come in and modify the effective chemical potential.
Yes, yes. So that is something that we are seeing in phase field. I think what he is telling is in the thermodynamics, thermodynamics.
No, that's what. So that is it's additive principle which works in the functional format. So you basically assume that or not assume, you basically have the solution thermodynamics, which is purely taking interactions of solutes, and then you superpose that with the elastic interactions as you model it, which will be including misfit stresses or any other stress effects. And the consolidated term will be the functional. And when you minimize that functional, taking care of all the dependencies of the composition, you should get the stress effects on the solution behavior that you will get from the system.
So only one caveat I will add, that is basically in a regular solution model, this is something that why I'll tell you, because on the aspect of segregation at boundaries, this problem came in. So if you have like a single phase, okay, and you have like a multi-component single phase, you have the different sizes, right? And so when you look at how these models, like these solution models developed in regular solution and beyond the regular solution, these effects, apart this, not the misfit effect. Misfit effect comes because of the phases, right? But but I am not talking about the misfit strain effect, but other than misfit strain effect, this is like solid solution effect, right? That is already included in the omega.
Yeah, so that can be included again as a superposition principle.
Yes.
Where you have the where you write down the solution thermodynamic without that term, and then you put misfit.
That's what we exactly did. Yes.
And then you create a superposed functional which will have all the stress effects again.
Exactly.
So does that mean that you can actually say, for example, most of the times you see phase diagrams at constant.
Yes. So you can modify the modified phase diagram as a function. You
can
modify.
Say apply a stress field, okay, on a model, use and solve the problem using phase field method, and now
so be very careful here. In phase
field there is a problem there.
Yes. Phase field method is the best method there, because if you want to derive the phase diagram, it depends on shape. There is a big problem there. The energy, elastic energy, is a shape dependent energy. Yeah, Guru, you can add.
So I was about to say that Johnson's paper and Alexander probably is a good place for Narasimhan Swaminathan to look at, because it is true, if you take the classical materials thermo textbooks, they are only talking about the chemical part of the bond energy. It's all EAA, EBB, EAB, etc. And then they think that there are two effects which come from composition. One is related to size effects that stretches or contracts the bonds, which can be thought of as the strain, and so you will add a strain energy term. But the moduli can also change. That is the minimum, about that how the well looks like. That also can change because of addition. And those are incorporated by generalizing the PV term by adding a stress times strain elastic energy. But this split is artificial. It is a continuum model where we assume that this split is possible. If you go do a first principles calculation, for example, you will not be able to neatly split it into chemical part, modulus part, and strain part. But on top of it, even when we do this splitting very nicely, there is an issue with the elastic energy because it is configuration dependent.
Yes.
Okay.
Same volume fraction can give different. So this breaks down the classical turbo, and that is what is described nicely in Johnson and Alexander's paper.
Is there what can I? Would you mind just sharing?
I'll mail you those set of papers.
Yeah, I can also share. In fact, Johnson and Woodis has also worked on it extensively.
Is this W.C. Johnson?
Yeah,
W.C. Johnson, yes.
Yeah.
However, one thing I'll tell you, phase field that way is a very good model because it does not care, it does not constrain your configuration. It does not tell that sphere has to remain a sphere. Sphere can change to plate, right? That's what. So that way, in phase field, it, as Abhik also pointed out, it comes very natural. It is like an.
But Shashwat, still that uniqueness that I give you the composition, volume fraction, and so what is the phase diagram, that still breaks down.
Yes, that breaks down. That is the problem.
But one system will not have the one single energy. No, it is multiple
energies.
energies.
Exactly. It will have multiple energies depending on the shape. Yes,
exactly. So all the lever rule breaks down. That's what Johnson wrote, right? So you can't construct the phase diagram properly. So
yeah.
Okay. Thank you very much. Yeah. I think I have to read that paper. If you share it with me, that will be great. Thank
you. Yeah, I'll send.
Yeah.
Okay. Any more questions? There is Uday whose hand is up.
Yes, sir.
Yes.
Sir, can this model accommodate the bimodal precipitation?
So that's a very good question. This is still isothermal, but we can include, as I told, as Avik also wrote in his paper, if I include the slopes and temperature dependence, then we can basically do this continuous cooling type of transformations, and we can basically also step change wave also I can do bimodal precipitation. It can do, yes. It can do bimodal. Means what you are trying to say is that that at certain temperatures some precipitates have formed and they're growing, and then you guys go below at certain temperature and you get finer precipitates. That's what you are talking about?
Right? Yes, sir. Yes.
Yes, absolutely.
And actually, sir, even on in case of just for example, for inconal 718, gamma prime and gamma double prime both are precipitating in particular temperature range.
Right.
So Uday, so one of the modules we are developing as the multi-physics modules development is having temperature and chemical potential or composition equation and phase transformation all coupled together. Okay. Yes. So because this is a problem where the temperature evolution is typically happening in length scales and time scales which are much ahead of. I mean, they are much different from the relaxation time of what your diffusion of the other mass is going to happen. So because of that, you need solvers which are able to address that problem, and that's where we will take care. Utilize the multi-physics solvers, particularly for these problems where the temperature is changing as a function of time and there's evolution, the spatial evolution of temperature. Now, for smaller samples where the temperature non-uniformity is not that much, there we can utilize these solvers again, where the temperature remains uniform, but temperature in the whole domain becomes a function of time. And that then can be again done coupled, as Shashwata was telling, by putting in the temperature dependence in the free energies, and that should be able to address the problem of multimodal.
Multimodal precipitation. In fact, here itself you can do it if you can give that free energy coefficients as a function of temperature and modulus.
So that's going to come over there in the next releases.
Yeah, it will be there.
Okay, sir. Thank you so much, sir. One more thing, means I just want to know opinion. During suppose that two precipitate of different shape and size, they are evolving at the same time, and what is the stress, means both will create some stress field, and how this stress field will interact is there any What is your opinion on this?
That's a very good question. What you are trying to say even exactly in coarsening, the diffusion fields as well as the elastic stress fields and stress fields and the strain fields overlap, right? So it becomes very nonlinear. Okay, so you cannot analytically solve this problem. You can do this here, right? I showed you in the multi-particle case. You automatically it takes into account these interactions, and because of these interactions, how things will change, right? The shapes will change. All right, so that you can do.
Okay,
that's
sir.
what you
thank
are
you so
saying,
much.
Yeah.
Thank you
So
so
please
much.
understand, these become, as soon as things overlap, as soon as things become multi-particle, it is no longer a single particle scenario. Multi is very different from single. You get the point, right? So how near or far they are, and as you evolve, you cannot even linearize these models, right? This automatically becomes very non-linear. So what happens is what you actually see in the simulations is what should happen, right? Given the physics.
Sir, thank you so much, sir, your advice, and I will be in the touch with you for.
Yes, sure, absolutely.
Okay, sir. Thank you so much, sir.
Yeah, thank you.
Okay, any other questions?
So Ram
has a question.
Yeah, Ram.
Hey, for this transformation-induced plasticity kind of cases, does this drag plasticity is expressly factored in?
So that is what I want to tell you. If we want to introduce plasticity, we do not currently. I do not have that solver, but it is very. See, as long as it is small strain, we can include any type of plastic strain, and that constitutive relation that basically means anybody can, means not only me, means anyone can basically include this type of strains, as long as you know the constitutive relation, how this plastic strain evolves as a function of stress. Okay, it can be like as a function of von Mises stress, and because that will be again added as an additional eigenstrain, right? So and the homogeneous strain will automatically be adjusted, because you see elasticity always gives rise to some volume change. Now, if you look at plastic strain, there is like we are always assuming incompressibility. So as a result, you are taking away some of this volume change by doing this shape change or in plasticity. So this can easily be, means it can be just a simple subroutine in small strain. However, as a previous question was now about this large strain deformation, when you go to trip and all, there may be very large, means you cannot do small strain assumption anymore. It's like finite strain. So finite strain requires a quadratic term to be solved, which again can be done iteratively. That's what Eisenlohr and others have shown in the mask. But I haven't included it, and I think, as Abhik also told, this is a research problem when you go to large strain. So we can do it as a research problem, but not as a part of this MicroSim development. We will use the MicroSim tools and we can interact, but I think not in this phase that we will go to large deformation mechanics.
In principle, the toolbox could be customized to address this problem. I mean, as you said, you're not
absolutely, yes. But remember, we do not yet have a finite strain solver. Finite strain, the problem is that finite strain you cannot directly solve, right? Using this Green's function method, you have to iterate, exactly like inhomogeneous elasticity solver. In fact, that also is not that difficult. But I think that we have to first explore what is the effect clearly. There are very few papers, first of all. We don't really know whether things are going on correctly, and we require to study it. It's a research problem. That's the idea. Which any person can, you can take my code and do it, and anybody can do it, and that will be nice, and we can collaborate also. But what I am trying to say is, will not be a part of this MicroSim tool in this first release, right, Abhi?
Yeah. So essentially, the idea is to give already established tools into them and give them a platform for people to modify and so on. But wherever new ideas have to be put in, tested, and so on, there we will first have a research phase. Then we iron out the issues, and then we put it into the software. So
yes. So, but it is possible. It's a very good thing that you and Narsimhan, both of you raised this point. It's a very important point. It's a very active area of research.
And as a pack, I mean, as an overall package, this is developed as a standalone tool or a standalone software, or
all these 4 problems that you see, brand potential, KKS, CUDA, then this OpenCL, OpenCL certification, all the OpenCL solver, all these are 4 in-house solvers that are packaged in one. Yes. Each can be modified independently.
And using
Ram,
this,
there already exist FEM based solvers. That is why we are not touching FEM.
So I mean, if FEM solvers are there, what we'll try to do is
we are using the others.
So we'll try to basically port them into other discretization methods and put a solution that works.
And if you look at Prism's SF, they solve some 24 problems or something like that, right? So,
right.
So this is along similar lines.
But one thing I can tell for sure to all students also, ours is much more massively parallel in terms of system size. You look at Prism simulations, you look at Moose. I have used Moose. I can tell you that they can do massively parallel simulations, but their system sizes are much smaller than what we can handle even now. So this is something.
This is coming because of the FEM has a large overhead in terms of memory.
Yeah, that number of DOFs increased so much in the Moose that you will see that in 3D, even like 128 cubed, you will find that it becomes almost like untenable with the computational resources you have. You require, like, every time you require 20,000 CPUs then.
Right. I mean, the perspective that we have is slightly different. We want to give a generic solver, which is multiphysics, and essentially where you won't have to do too much work to make it work for a particular physical problem, and get it running. And the idea is the tools are going to allow you to use all the NSM resources quite readily. So that's essentially the motive. So that way we differ from Prisms and Moves in the perspective. They are based on just multiphysics solvers. So these are just multiphysics libraries. We want to give a multi-phase solution, multi-phase, multi-component phase field solver. So our focus will always be on the phase field part of it and the generalization of phase field.
And this can also be used as a library instead of a standalone.
Parts of it. So parts of the things can be used as libraries.
Yes. Yeah, parts of the thing can be used as a library. Yeah, I think what you are referring to is like, can the solvers be directly called in your routines like that, right?
Yeah. So some functions can be. Modules can be called upon. Yeah.
Absolutely. It can.
So essentially, you can develop the module. Each of these solvers, if you want a particular part, you can customize that part for your code. Essentially, that's why it's that.
We ourselves, by the way, we ourselves are doing it. For example, say Abhik has written some function, we just take it and then use it. Sometimes we don't write it, right? So that itself is happening, right? Elasticity solver. I don't think we will write 4 elasticity solvers. So that's right. So that way these are very modular. Or for say thermal. See, if I want to do the temperature evolution, I will directly take a Abhik solver.
Okay, I mean that's nice to hear, because I mean one of the things, as Abhik was pointing out in the very early thing, differentiating it from open phase and other open source phase field, particularly phase field related ones, digging it deeper and opening the code and adapting things for yourself is not an easy thing. So I was just wondering how easy it will be.
Remember, here the focus is developing a phase field solver. Moose or Prisms had a slightly different focus. Their focus was to apply FEM to solve phase field problems as a separate module. They also solve other multiphysics problems. So as a result, ours is more like phase field plus other multiphysics things. Phase field is like the primary focus.
Ram, to answer your question slightly differently, these are solvers are you can think of as function calls. So you can take those functions as long as your interface gives the same information, you will be able to reuse them in your.
Exactly, you're right on the point. For me, when I was trying to open up open phase and trying to see whether I can customize it joke to do that. So
So probably, I mean, based on your question, like what these Sparks and Lamps people do, how to use this as a function call, as a library, we can even put some notes for people who want to use it like that. That this is the function,
so
this
just
is the
to
input it takes, and this is what it will give you.
Just to aid in this discussion, we will be having a separate developer workshop in a few months or so, where if you we'll basically discuss these things. When you want to, let's say, some parts from the code or modify some parts, add your own user-defined parts. This is something that we will give a small workshop on.
Only thing I will request before we arrange for the workshop also, you start doing that and you contribute it as open source. So as a community, MicroSim can grow and it can basically already you can see the capabilities. So it can grow as a community. There are so many problems that people are asking that can be solved. I think that way it will really go much far ahead than other things that are existing.
Okay, so I think
there is also a question in the chat.
Yes. I think I'll take the questions at the later because we will have to. Are you accepting pull requests? Yeah, you can. I mean, presently it will be a different branch. We will essentially look at your contribution and then accept the pull request. All right. So because I mean, we'll have to just look at what the developments before accepting the pull. All right. So in the interest of time, can we just go ahead with the last presentation?
Yes, I think so.
And we'll have a slightly extended discussion just after it, right?
Okay. Yeah. Thank you.